This talk will not be in Russian. It'll be about hardware-based tracing on ARM. So let me start out by who I am and why I'm giving this talk. So I'm the founder and director of ComSecures. We're a boutique consultancy in Germany, and we do mostly work in embedded, automotive, and mobile. I have a background in cryptography, but that's not relevant for this particular talk. So I'll give you a brief overview. We'll start with motivation, why I think this is an interesting topic. I will talk about the use of core site tracing in embedded development and what the status of core site on Linux is. I will talk about various hardware choices that we made, that we tested, and things that didn't work, basically failures here. I will talk about auxiliary cores on SoCs. So many systems on a chip these days have more than just a couple of cores for running the main application, but they also have auxiliary cores, for instance, for video decoding and stuff. I'll talk about how you can use core site tracing for that. And we'll also briefly look at core site and other things for tracing on iOS devices. So the purpose of this talk is to get security people interested in technology that has been widely used in embedded systems development already. So tracing on these systems in the past was done using hardware probes until recently. By recently, I mean like this changed in the last 5 years. That's what's meant by recently. What happened was that at that point, the majority of SoC vendors started integrating technology into their hardware that allowed to do the tracing not just purely using hardware-attached probes, but also in software as well. So you basically have a software-based hardware tracing where the tracing of the program is done by the hardware, but the capture of the information is done purely using software without doing any soldering on the device. However, systemically, the number of parameters of things that can go wrong is vastly bigger than on Intel. So Intel has a similar technology these days. It's called Intel Processor Trace. But with Intel Processor Trace, you can be sure if you buy say a Skylake or later generation processor, you will have Intel Processor Trace and that'll work for you. This is not the case for core site. I will also try to motivate you what applications for this are in offensive security. So one very obvious application is branch coverage guided fuzzing. So in a lot of cases when you have closed source programs, the problem is that dynamic instrumentation doesn't really work. So the libraries available for instrumenting closed source on ARM, and especially ARM64, they don't work so well yet. And the other option that you have is you can run everything in QEMU, but then you have a significant slowdown. So we have done that in the past for customers of ours. Slowdown is about a factor of 7 to a factor of 9. The second thing that you can do if you are attacking DRM, there is a technology that has been used by Riscure, I understand, for a while, and it has been recently been published by people from Quarks Lab, and I think someone from NXP at the time, which is called differential computation analysis. So this is basically side channel analysis in software. If you want to do this, you can use core site as well, but what you will need in this case is a so-called data value trace, and this is not available on all of the cores that are out there. The next application area would be SoC firmware security. So, as I said before, like there's a lot of processors, especially in mobile phones, that have not just application processors integrated, but also other cores for wireless, for GPU, video decoding. And it turns out that these often have core site technology for tracing integrated as well. Last but not least, it's not related directly to offensive security, but it would be nice for for exploit development to have reversible debugging on ARM and on ARM and ARM64 as well. So RR works really great on Intel, but they don't have support for ARM at the moment. They've looked into whether they can use similar tricks with the PMUs on ARM that they do on Intel, but that doesn't work. But it's unlikely that they will go the core side route as well, because it's too hardware, like you will tie yourself to a very specific model of hardware, and they don't want to do that. They want to have something more generic. So what exactly is ARM Core Side? So ARM Core Side is a family of IP cores that is licensed by ARM to silicon vendors. So it's an on-chip debug and trace technology. So debug in this case means that you can set breakpoints or watch points, and tracing means that you basically extract information about the program flow. Can be integrated in all of the Cortex designs except the M0, so from the M3 to the A73, all of these are compatible with various core side blocks, and it's comparable to Intel's processor trace. It's a successor of embedded ICE that was the standard on previous ARM generations on ARMv6. So the evolution of hardware tracing is that in embedded development, you used to have separate TPIUs. So these are trace port interface units that connected to a dedicated port on your development board. And then you would have trace data clocked out. For this, you have a 30-pin, usually a 30-pin interface, so-called MICTO connector. These things are stupid expensive for like silly cables. And the problem is that once you start increasing the clock speed, the synchronous clocking out of things becomes a little delicate. So what they then started doing is they integrated buffers into their designs and thought about like how to compress the traces. So originally, they basically dumped like each instruction, the PC for each instruction that they executed. So next evolution was basically integrated a buffer and record less information. So this is the so-called embedded trace buffer. So this is a small dedicated piece of RAM for trace data that can be read out using JTAG. And the alternative to that is if you don't want to do that using JTAG because you're just constraining the number of signals that you can have, you can also use serial wire debug, and serial wire debug has a dedicated pin for outputting that trace data, which also will be compressed. We'll talk about that on the next slides. So this would be a setup for hardware-based tracing that's sitting on my desk in the office. So this is an OpenQ820 development board. That's a Snapdragon without a modem. Well, actually, it has a modem, but it's disabled. And attached to that is a Lauterbach Trace 32. That's a commercial JTAG debugger, which is pretty powerful, but pretty expensive as well. In this case, I'm using regular JTAG to extract the data from the system, because this one doesn't have a MICTO connector. We have other boards with MICTO connectors as well, but I can't show them because they belong to customers and we're under NDA, so this is like a board that I personally have. So what can be traced? So there are two areas. You can do instruction traces, so-called program flow traces. What this means is that you record so-called program waypoints. So this is any instruction that potentially changes program flow. So this can be branches, indirect branches, but also return from exceptions. And there are bits actually for also making barriers waypoints. The other thing that you can trace is data. And there are two things that can be enabled in the core. The first one is data address trace. That just tells you, hey, someone loaded from this address. But what you usually want, you want to have the data values that are being loaded or stored as well. And the problem with this is that this is only available in less complex cores. So basically in the lower ends. So in the Cortex-A5 and the Cortex-A7, it'll not be available in the high-end cores because it's too complicated. So in the ARMv8 cores, you almost always see that data value trace is turned off. So let's talk about the components that you can have. So there's 3 different kinds of components that you have in a core site design. There's sources, sinks, and links. So sources that we care about are ETM and PTM, which are basically the same thing by a different name. So these are embedded trace macro cells or program trace macro cells. There are also system trace macro cells and instrumentation trace macro cells, but these are mostly useless because they're just basically for if a developer wants to instrument his program himself during build time. So basically, it's like a glamorous printf debugging built into the system. So you can have a dedicated port for your printf debugging output. Then you have the sinks and the links. This is incorrect. So the next thing is actually are links, not sinks. So funnels, replicators, and ETRs are links between different components. These connect different things. So a funnel basically is something like a multiplexer. A replicator is something that just makes multiple copies of something. And a router can do stuff like put things into RAM, like into DDR, or like not RAM that is on the actual chip itself, but like external RAM on a bus. And then you have sinks, and sinks, for instance, are these embedded trace buffers, but they're also the trace port interface unit, and the so-called embedded trace FIFO, which is basically a FIFO, so similar to the buffer. It's just like a little bit different in how you have to read it out. So an example core site architecture. This is a picture from the ARM DS5 documentation. So you basically have an ETM or a PTM attached to each of the cores. So this is slightly unusual. I think this is just to show that you could do this, but you wouldn't do this. You wouldn't attach both an ETM or a PTM if it's the same type of core that you have here. So maybe it's 2 different cores. Then you have the system trace macro cell. You have a bus with a system memory attached. You have a peripheral bus for the debug. And you have something that's called the cross-trigger matrix. And this is something pretty powerful as well, because you can basically program core sites such that you start recording at a certain point, and then only if a certain instruction has been hit on one core, you can make sure that the tracing happens on another core. So you can build things like this. And this is what the cross-trigger matrix is for. And this ATB bus, this AMBER advanced trace bus, is basically where you pump out the data at the end. In this case, you pump it out to a buffer. No, not to system memory. So if you would have an ETR, you would basically pump it out to the ATB, and the ATB they would then pump it to the ETR and then to system memory. Okay. So now the question is like, how do you identify components for a given SoC? So the most obvious thing is you read a manual. The problem is most of these manuals are only available under NDA, and sometimes different versions exist, so the public version will not contain information about the different core site components that are integrated. Option number B, your SoC is supported by Linux, and the vendor or someone else was so helpful and has added the components to the device tree. This unfortunately is not very often the case. So in mainline Linux, I think except for development boards, the only example that you'll see is for like a very low-end Chinese mobile SoC. It's a Spectrum, I think 9836. And in vendor trees, the description for core side components in the Qualcomm repositories for their chips is fairly complete. But that's about it. Option number C, if you don't have device trees, there's something called the core side ROM table. So this is basically a table in memory, a structure that describes all of the components that you have in the system. And if you know the address of this ROM table, then you can basically dump what you have. And oftentimes, when you attach like if your JTAG debugger, your hardware JTAG debugger, knows about the CPU that you're debugging, so if it's supported by DS5 or by Lauterbach, you will see where this ROM table is located when you attach. Otherwise, you can try scanning the whole address space, but this is painful in my experience. So the ROM table gives you a tree of components, and then you have like a component ID and a peripheral ID, and this you can basically map to what the component is, and it gives you the offset to from the ROM table base address to basically the memory mapped I/O for the device. So basically, if you have a ROM table at say 8,000 hex, and you would have an offset of 100, then you would know, okay, the peripheral that I'm looking for is at 8100. And I can write to there and configure it that way. Device tree is basically a tree of named nodes with property describing the hardware, and that's usually stored in flash and then passed to the bootloader for the operating system. There's also ways to lock core side down. This is mostly like most of the concerns here are about two things. First of all, about invasive debugging, which we do not care about at the moment. So, like, invasive debugging means that you actually attach a hardware debugger to be able to set breakpoints and to read out stuff at runtime. And so that's the first concern is invasive debugging. So you would usually have that disabled on smartphone SoCs. And the second concern is secure debug. So if you look at ARM, you will know that there's a technology called trust zone. So you don't want code that is running in the secure world to be traceable by code running in the non-secure world. So this is why you usually set these register bits to not allow secure, non-invasive debug, which would be core side tracing of secure world code running. In terms of software, if you want to do this like yourself without support from a kernel, there's a great open source library that ARM published in January this year. And basically that allows you to utilize all the different core side components from the bare metal or through DevMem. And the number of supported boards is a little bit oddish because those are mostly like older development boards. But extending this is pretty trivial. Like if you have the configuration, it'll take you half an hour to an hour to add another board. It also contains a nifty little utility called CSLS. So if you know the address of the ROM table, you can dump this and then use the dump to extend for your board. And there's some nice demos for standalone tracing in there as well. So when I set out to get this technology to work, there are a number of things, there were a number of hardware devices that I tested that didn't work. So, I mean, the most widely used Tinkerer device for ARMv8 these days would be the Raspberry Pi 3. So that would be an obvious first choice. Problem here is there is no public docs on core side for this core. So it's a Broadcom 2837. And I attached a JTAG debugger to Raspberry Pi 3 and looked at the ROM table. And the component IDs, they don't match anything that's known to be like a core side component that would allow tracing. So to me, it looks like this is a dead end for core side tracing. Then I had a Chromebook with a ROC chip, which is actually a pretty nice CPU. I didn't expect that. And there's a public technical reference manual that is fairly complete. And it also describes the core side arc. But for some reason, they decided to skimp on the buffers. So you can do hardware tracing through the TPIU, but they didn't integrate any buffers or routers or funnels. Then I had access to a machine running a Cavium Thunder X. And I was like, this would be nice for fuzzing, 48 cores. Then the first bummer was, okay, this thing doesn't support ARMv7 anymore, it just does ARMv8. And the second thing was the TRM is only available under NDA. Okay, well, I know someone who has signed such an NDA, maybe he can look something up for me. And it turns out there is no core side integrated on this as well. But I mean, after thinking about this, this actually makes sense because they want to integrate, they want to use the die space for performance, so they don't want to integrate additional silicon that doesn't give them like another core. So this is like basically waste for them. So test hardware that has been working for me, besides various phones, was a Dragonboard 410C. This is like a pretty cheap development board that has 4 Cortex A53s. But it's oldish, like it's, I think, 4 years old now. And the problem is that I have observed some trace lossage there. So this means like basically I'm seeing buffer overruns. I think this is fixable though. Slightly more powerful is the OpenQ820 development board, also a Qualcomm CPU. This has 4 Creo cores. These are proprietary Qualcomm cores. And on this, I don't have trace lossage. But it's like, that one is $550. So if you want to scale up, I'd rather figure out why I can't get, like, what I have to do to make the trace lossage disappear on the cheap board, and then buy like 8 of them instead of one of the more expensive ones. So what many people don't know is that CoreSide is actually supported through the perf subsystem in Linux these days. So this started in, basic integration of the drivers started in Linux 3.19, which was funded by Linaro. Linaro also backported to 3.10 and 3.18. You might recognize these versions if you are looking into Android. So these are like widely used kernel versions by various SoC vendors that they base their Android kernels off. And then the integration into the perf subsystem of the hardware drivers started with Linux 4.9. So basically, if you're on a lower version and you have just the drivers, you can still use that, but this basically means that you have to configure the core side tracing manually through the sys file system. You can do that. Perf is a little bit nicer, but there's also like a dependency issue. So you need a specific version of a library and perf and the kernel for this to work. So support for a given device now depends on like the kernel version, whether the chipset vendor has integrated ETM support both into the hardware and into his, whether there's a driver for that. Then it depends on whether the core side elements are discoverable and whether access to core side debug has been enabled or, well, has not been disabled. Okay, let's see how this instruction trace works. So this is the so-called program flow trace. This is generated either by the PTM or the ETM. And the nasty thing is that these are different formats that you end up with. So I think the logical progression was there was an ETM version 3, then there was a PTM version 1, PTM version 1.1, and now we have ETM 4 on ARM64. So this is the format that they use is packetized. This is output over the ATB. And basically each of the atoms indicates a waypoint instruction execution. And the atoms that you have is basically you have an E for a branch condition that has been checked. A branch condition that has been passed, and an N for a branch condition that has failed, and a W that indicates a cycle. And then you also have syncs, and all of this is assembled into variable length packets. So these cycle indications are if you really care about performance, you want to have cycle accurate tracing on your platform. So not interesting for us. This is what an example trace looks like. I think this was just an Alice that I executed. So at the beginning, you see like a synchronization happening. Then you will see, okay, this is the address where I'm at. So in this case, this is decoded from the physical address. And then you'll see an F3 atom. An F3 atom basically is 3 different waypoints encoded into one atom for you. So it basically means a branch condition has failed the check, and has passed, and has failed. And you see more of these atoms, and then you see another synchronization. And what you'll see as well is you also see we're running in EL0, so we're running in user mode, and we're running in the non-secure world. And then, whoops, we'll see an exception. And we see that we have just transitioned we should have transitioned from user mode into kernel mode. And this basically keeps on going as long as you have RAM to write to. So I thought, okay, if I can do this, how hard is it to actually do something useful with it? And the first thing, obviously, that comes to mind is like, okay, let's try to integrate this with AFL. But there's also another fuzzer that already has support for another hardware tracing technology that is also available through the perf subsystem. And this is HongFuzz. HongFuzz is written by Robert Zwiecki. I don't know how to pronounce the last name, sorry. This is also an evolutionary feedback-driven and coverage-based fuzzer. And like extending this for core side through perf was really easy. This is something that you can do in a couple of days. However, it's at the moment somewhat inflexible because it's tied to the specific hardware that I'm using. I'm making some assumptions. So I plan on releasing this, but I have to make it a little bit more flexible here. So it basically assumes like that you have an embedded trace router and that you have an embedded trace FIFO and so on. And I have to like have some description language to let the user specify what he actually has. Otherwise, he will be tied to this particular board. And it only supports ETMv4 trace decoding at the moment. And I'm using OpenCSD for the trace decoding. And I think this is not really optimal as well because this library it's good, but it's not optimized for performance. So, like writing this by hand would probably be faster. Okay, so this works, but still needs to be improved, and that hopefully I will be able to release this in the next 2 weeks or so. While I was looking at device trees, I noticed something interesting. As we know, there's all these different kind of cores that people have in smartphone SoCs these days. And many of them are ARM, except for the GPU, obviously. But hardware accelerator for video decoding often are ARM. Wi-Fi, in some cases, are ARM cores as well. Motion sensing are usually our Cortex-M cores, and GNSS cores are ARM as well. So while I was looking at the device tree for the for the Dragon board, I noticed that the device tree also talks about ETM that they have for other cores in the SoC. So the first one is the so-called RPM. That's the resource and power manager that's used for bring up. That's not so interesting. But the input number 2 is ETM for the modem. And in this case, this is not actually an ARM, but this is a Hexagon CPU on a Qualcomm. And this apparently supports ETM as well. And I looked into Lauterbach because I have an older Trace 32 license that also allows me to debug Hexagon. And it does, like, you can actually get ETM from the modem for Hexagon as well, from the Hexagon core. And you also have a funnel that connects to the wireless component. This is not actually widely used because on the higher end smartphones, people usually integrate a Broadcom, but on the low end Qualcomm phones, you have a so-called WCNSS, and this is a core that would also expose an ETM, and this is unexpected. But Qualcomm is not the only SoC vendor. After I saw this, I looked at Huawei and Samsung as well, and they have similar things. It's not as visible in the device tree. You basically have to look at all of the header files, but you'll see that they have integrated tracing technologies for the other cores as well. Whether or not you can access it depends on the device again, because sometimes these memory ranges are then only accessible to EL3 or Secure World code. Okay, so that was the Android side, and I think when I started looking at this, I noticed that there were core side strings in the iOS kernel as well. And meanwhile, Apple has released the ARM parts. So at that time, you basically had to reverse engineer the functions. And what was visible to me was, okay, this may or may not have something for core side debugging, but it looks up something in the device node and nothing is there. I don't know what's going on. Now Apple has released source code, and it looks like, yes, they do have core side tracing support, but only on non-production devices. And I have looked at device trees for various iPhones I have. So since iOS 10, the device trees are no longer encrypted, and there are no indications of these the components that they're trying to look up in the device trees that I have. So I suspect they exist in development devices. Whether you can use like knowledge of these address ranges to get the same thing on production devices is not clear to me at the moment. However, I also noticed that because like when you look at Xcode can do tracing, and the question is like, how does it do that? And then you look at the developer disk image, and the developer disk image has a little tool called iProfile, command line tool. And if you look at that and the library that it uses, you'll see that you actually have access to PMUs, so performance measurement units for tracing, and that actually works. So this is an alternative to core side that you can also do on Intel. So these are registers that are exposed to the coprocessor 15 or optionally memory mapped. And there's a talk, I will not go into this because there's an excellent talk at Recon 2016 where Matt Spizak used this for hardware-assisted rootkits and for instrumentation. And this is like supported on ARM v6 already, and it's available on many Android smartphones and on iOS. But it's a different approach. Like you have to do slightly more work to capture traces. And my interest was in core side. Okay, so these are resources that you should read if you want to know more about this subject. And yeah, if you want, I can show you some demos of how you would actually, because this was a very dry talk. I can show you demos like how you would actually configure these things under Linux. I don't think there's much of a use in like letting you see a fuzzer running, but that will be released in approximately 2 weeks. So if you want to see demos, I can do that. Otherwise, if there are questions, feel free to ask.
We want to see some demos.
Okay. Has a syntax where you need to specify basically where you capture from and where you route things to, and we're just now capturing the ls. And as you'll see, like this is like one of these trace losses here. This is particularly bad. Usually you have approximately 10% loss. So this is the second trace, wait, what? Okay, so this was a performance measurement. So what you will see, okay, so the syntax that's being used here is for only recording userland, and what you'll see is if you record if you record a trace, even though it is hardware, it's done in hardware, and even though you shouldn't have any overhead, due to the fact that the buffers have to be configured, you end up with an overhead of approximately 50%. So I think this was, sorry, this one was incomplete. So this is let me go back, sorry, this was too fast. Sorry. So this basically dumps the perf capture as a raw buffer as it was recorded into memory, and this then is the decoded trace that you get. And actually not sure whether I have the right demo videos here. Yes. So what perf will also do for you is it'll, if you have symbols, it'll also decode the symbols for you. But this is like the demos here are mostly showing like how you would use perf for doing normal for normal debugging on the system. And yeah, I think we should stop here. Sorry. So that's it. Sorry. I think I had the wrong demo views here. I'm sorry about that. Okay.
Hello. Thanks for your talk. Did you try this on high key? Make a high keyboard.
No, I did not try it on a high. I know the development boards, but I did try, and this is something that I cut from this version of the talk. I did try it on a Huawei P10 Lite, which is a very similar CPU. Like it's also a high, 62.
High silicon, yeah,
yes,
62.
Family, and tracing works there with some oddities. So, for instance, if you try to dump the ROM table, you sometimes get synchronous aborts, which I haven't been able to figure out why these things happen. And the buffers are somewhat on the smaller side. So, yes, you can use this if you want to use the CSAL library. There's no support for using the perf subsystem on this one because the kernel is lagging. You could probably port things backwards though, or use CSAL basically. But the basic drivers are there. So also if you want to like configure things through the device nodes, you can do that as well.
Okay. Thanks.
Thank you. Very interesting talk. Could you please tell me if it's possible to trace the trust zone code in ARMS?
It is if it's not correctly configured. So basically, if the authentication, if this auth status has the bits for non-invasive secure world debug set, then you will be able to trace trust zone code. But of course, no silicon vendor would ever screw this up, right? Right.
Okay, thank you.
And also, I was kidding about that. More questions? Okay. Thank you.